bending moment, but there might be some questions on your understanding of shear and bending moment diagram. So first we'll go through the analysis of portion using the standard equations, and then we'll go through the drawing of shear and bending moment diagrams. Then we'll have some examples. Okay. I think this more or less says what I just said. For the most part, deflections and rotations of beams on the exam can be calculated using standard equations that we'll go through, and that's true for shear and bending moments as well. But like I said, that there might be some questions that test whether or not you understand shear and bending moment diagrams and their usefulness, or be able to, if you're provided a shear diagram, for example, be able to understand some characteristic of the bending moment diagram that would be associated with the same beam. One thing that's important in the analysis of beams is the principle of superposition. Essentially, any type of distributed or concentrated loading can be broken up into certain standards, and then the combined effects of those loads can be superimposed because these beams are linear elastic systems, and therefore you can superimpose the simultaneous actions of one or more loads, or two or more loads. Am I the only one who has this problem?
This point, like in truth, yeah, because the computer is there.
Yes, it is. Okay, so here are standard equations. For example, there are cantilever beams with a concentrated load at the end. You also can have, in general, a cantilever beam with a concentrated load anywhere along its length. You can have a uniform distributed load along the length of a beam. You can have a linearly varying load, distributed load across a beam, along a beam, and you can also have a concentrated moment. In general, the types of things that are asked for is the slope at the free end, the deflection at any point, and the maximum deflection. In general, the maximum deflection and the slope at the free end are the most commonly requested values to be calculated. We talked last night about the bending stiffness term, EI. You see that that comes up in each of the equations for deflection and slope. So you're given a problem. It's basically it's a process of identifying which of the standard cases that it applies, and then substituting in the particulars for the problem. All right, you changed? Okay. You can also have a simply supported beam, as we talked about yesterday. In order to have three equations of global equilibrium, these tend to be shown as a pin end and a roller end. Again, you can have a concentrated load at any place along the beam. You can have it at the middle of the beam. You can have a uniformly distributed load, or you can have a linearly varying distributed load along the length. You can also have a moment at the end. Same thing, the slopes at the ends and the maximum deflection. In general, for the cantilever beam, the maximum deflection occurs at the free end. For a simply supported beam, the maximum deflection occurs at the center of the beam. So those were equations when you're being asked for the deflection or slope of beams, or the slopes at the free ends. You can also have a set of problems that are asking for the shear and the bending moment. It's the same, but it's the same process. You identify which general case you have from the standard set of equations, and then you plug in the problem-specific values. Couple things of interest here. You notice that the EI, the bending stiffness term, is only in, shows up in the deflection problems. It doesn't show up in the shear and bending moment equations though. In general, when you have a simply supported beam and symmetry to your load, the maximum moment occurs at the center of the beam, and the maximum shear occurs at the points of reaction and are numerically equal to that reaction. You can also have a problem that has a uniformly distributed load that does not extend for the full length of your beam. Same thing, you're just going in at the, you're finding the problem, the general case that fits your problem. That this is the case, this is a concentrated load at the center, concentrated load at any point. If you notice here, when you have a concentrated load at the center, what are and that's the only load you have, what are the support reactions going to be? The support reactions will have to sum up to the value of the concentrated load, and because of symmetry of the concentrated loads at the center, the two support reactions will be the same. They'll be the concentrated load divided by 2. You notice here that essentially, as the concentrated load moves back and forth, if it's all the way at one end and lines up exactly with your support, then 100% of the load would be taken up by that support reaction, and there would be 0 over here. So what really happens is, as that concentrated load moves back and forth, the ratio or portion of the load that's carried by each support reaction is linearly proportional to the distance. So the closer it is to this end, the larger portion of the total concentrated load is carried by that end. And you see that's what's happening in these two equations here. So for that problem, you don't even really need to see the equation. You know if you have a concentrated load at the center, 1/2 of that load is carried on each side, and as it moves either way, the percentage of load that's carried by that end is proportional to how close it is. Here you have a uniformly distributed load. Okay. Well, not a uniformly distributed load, but a linearly increasing load. I'm sorry. A cantilever beam with a uniform load. In this case, because you have a fixed cantilever end, all of the moment, or the maximum moment, is always going to occur at the fixed end. And the moment at the free end will be 0 unless there's a concentrated moment applied. The maximum shear is of course also at the fixed end, because that's the only place that can support shear. You notice here, the total shear is equal to the total amount of load. The distributed load multiplied by the length. So when you're all the way at the reaction end, the shear force at that point is equal to the maximum load applied on the beam, which of course makes sense because that's where the load is all being carried. There's nothing supporting that rest of that cantilever beam. There's no other place that can provide that support reaction. The moment at the fixed end here is just equal to that shear multiplied by the moment arm, and that's how you get that. With a cantilever beam with a load at a concentrated load at the free end, of course, in that case, the shear is constant across the beam, because essentially what's happening is there is shear, there's a load being applied at the free end, and that load stays constant. It's there until at the fixed end where the reaction force basically where it's taken up by the reaction force. We'll see that when we look at when we draw the shear and bending moment diagrams. The maximum moment is of course just that concentrated load multiplied by the length of the beam. For a cantilever, really the concentrated load at the free end is just a special case. In the general case, being the concentrated load anywhere along the length of the beam, and now you just basically have a translational term, x minus a, which essentially modifies that prior equation for the concentrated load at the free end. It takes into account the moving of the load. That's what that x minus a term is. If you go back to the prior one, it's there. Okay, so here's an example. What are the support reactions left and right? Well, you can go into the equations. But what is this? This is a simply supported beam with a concentrated load somewhere along the length of the beam. We have a set of equations for that case. And it's these two here that I pointed out. And so like we talked about, you really don't even need the equations because this is the only load. You know it all has to be carried by these two supports. If it were at the center, it would be 1/2 each. But now we have it basically move towards this end. So the way to remember this is, well, this is a very nice example because they add up to 10. And because they add up to 10, these really become percentages. So because there's 7 feet here and 3 feet here, that means 70% of the load is carried by this end, and 30% of the load is carried by that end. Just the simple proportion. 3/10, 7/10. Here is a cantilever beam with a certain beam. So because it on the exam, if it identifies a beam, is going to provide you information like the moment, calculated moment of inertia for that beam type. Remember, there's one thing to remember is that the Young's modulus or modulus of elasticity of steel is 29 million pounds per square foot or 29,000 kips per square foot. Anyways, this is with a triangular load, and we're looking for the deflection at point A. Yeah. The linearly increasing distributed load is one of those standard cases that we have equations for, so we just go to that. The number one thing people make a mistake on in this kind of problem is the loading is given in terms of feet, and the modulus of and the moment of inertia is given in inches to the fourth power. So you either have to do the problem in terms of inches, or you have to do the problem in terms of feet. But the kind of mistake people make is they mix inches and feet in the values that they're plugging into the equations. So other than that, it's a pretty simple equation. It's the essentially it's the maximum distributed load. That's usually given in terms of pounds per foot times the length to the fourth multiplied by 30 times EI. So you end up, when you do it in terms of inches, you end up with sort of large numbers. You also want to make sure that you're using kips and kips or pounds and pounds. So really what you need to focus on is being able to identify the general case for which this particular problem is an example, and then find the equation. You're either being asked for a deflection, you're being asked for a slope, you're being asked for a shear, you're being asked for a bending moment, or you're being asked for a reaction. And you're going to have an equation for that. That equation, the inputs that input data that's provided as part of the problem statement might be a combination of some having units of inches, some having units of feet, some having units of pounds, some having units of kips. You want to make sure that you keep your bookkeeping straight as you work through them, like is shown in the example here. And if you do that, then they're very straightforward to answer. Here's an example of, it's probably a flagpole of some kind, but really all a flagpole is a cantilever beam standing on its side. So here we have a load of 10 kips applied at a height of 15 feet above the ground. The total height of the beam is 5 feet. It's fixed at the ground, so therefore there's a bending moment and a shear generated there. And what is the deflection and rotation at the point of the application of the load? Well, you'll find that there's a set of equations for a concentrated load at some arbitrary location along the length of a cantilever beam. And the deflection at that point is given by the equation PL cubed over 3 EI. Again, you just want to make sure that kips and kips, feet get converted to inches.
Well, that's the equation for the point load at the tip, not at the 10.
Oh, okay. Let me see. Okay, then what is that equation supposed to be?
you're supposed to hit time, or instead of dividing it by 3, it's divided by 6.
Okay. Okay, good, thank you.
So-
Yeah, so on sheet 90, apparently that there's a typo where that should be a 6 instead of a 3.
Well,
No?
yeah, well, looking at your wording, it says at free end. And so
Okay.
the question doesn't correlate to the diagram.
Well, hold on, because we will also on the next page, I think we're gonna do okay, so on the next page, we're gonna do the same calculation, but at the point of the concentrated load, I think, right?
Okay.
Oh, no, okay, no. All right, what is the deflection rotation at the point of load application? But then it gives the equations for the free end. I see why that would be confusing. Top. Okay. All right, well, so are we in agreement that what's wrong is these words at the free end here? Yeah, okay, so these shouldn't say at the free end, these should say at the point of load application. Okay, thank you.
Well, but then it's not an equation. I think it's correct if you say at the free end and not see if there's anything wrong.
What
Yeah,
do we do on the next page though? On the next page, we have equation for deflection of cantilever beam with concentrated load at the free end. So here we're using that equation, and which equation is that?
that's the one that correlates with the sketch.
So on this one, yeah. it's
So-
at the free end.
Okay. All right, well, thank you. Well, then a good assignment is to make sure you understand what is wrong about these two sheets. And if you don't understand it, then you can send, if you look through it and you can't sort it out, then like I say, always say you can send me an email. The point of this problem, though, is to show that the rotation of the beam rotation is the same at the point of location, at the location of the application of the load, and at the end of the beam. And that's because you have a beam and you apply a load, that load creates a rotation, but then you don't have any load here to increase the curvature. So from here on out to the end of the beam, it becomes a straight line. So you have a greater deflection at the end of the beam than you had here, but the slope at the point of application and the slope at the end of the beam are the same. So that's really the point that I'm trying to communicate with these two problems here.
That one is this, but you have it right, but this is the same three beams.
Okay, so this one is 0.96 inches, and this one is 1.44, so that tells me that this has to be the one at the point of application, and this has to be the one at the free end. And the rotations are the same. One thing also to remember, the rotations in these equations are given in terms of radians, and how many radians are there in a circle? No, there are 360 degrees, aren't there? 2 pi, right? Yeah, okay. So you convert between radians and degree using the relationship between there being 2 pi radians in the circle and 360 degrees. Okay, what is the moment at the midspan? So this is a problem that is trying to communicate the use of superposition. What you have is 7 kips per foot at this end and 5 kips per foot at that end, and it literally decreases. We don't have an equation. We don't have a standard set of equations for having a varying non-uniform varying distributed load across the full length of a beam that doesn't start at 0. But we do have one that is uniform. So really what this is the combination of two loadings. The first one being 5 kips per foot uniformly distributed along the length of the beam. And the second one being a linearly varying distributed load that starts at 0 and goes to 2. And we have a set of examples for the uniform distributed load, and we have equations for the linearly varying distributed load. So that's what we're showing here is you get the moment at the midspan for a uniform load of 5 kips per foot is 62.5. And then the moment at the midspan for the varying load that goes from 0 to 2 is 12.5, and then when you add them up, they add up to 75. So again, because beams are linear elastic systems, and these are linear elastic equations, then superposition can be applied. And here's an example, determine the support reaction forces, the maximum shear moment, and deflection for this beam. So really, this is an example that's asking for everything that you can ask for. The beam is 20 feet long, it has a pin connection here, it has a roller connection there, so we have three support reactions for static equilibrium. We have a uniform distributed load and we have a concentrated load. Well, whatever the beam is, that you might notice that for the use of these problems, the beam is entirely characterized by its modulus of elasticity and its moment of inertia. You don't even need to know what shape the beam has. All you need to know is that its moment of inertia is 3,000 inches raised to the 4th power. In general, a larger moment inertia means a larger resistance to bending, which would mean smaller deflections and more gradual slopes. So there's no horizontal applied load, so we know that that horizontal reaction on the left side is 0. Because it's symmetric loading, the vertical support reactions on the left and right side are the same. So basically they're just the total load divided by 2. And then you can apply the beam equations for concentrated load. You can apply the beam equations for uniformly distributed load, and then by superposition, you add them up. So you can add up the moments at the midpoints, and you can add up the maximum deflections. Now, do the maximum deflections happen at the same place? We know that they do because it's uniform loading. The concentrated load is at the center of the beam, and the distributed load is uniform. So therefore, we can simply sum these up knowing that they're both occurring at the same point. Shear and bending moment diagrams. In general, if you're given the load diagram, you can draw the shape, you can draw the shear diagram. Shear at any point is equal to the sum of the loads and reactions from the point to the left end. So, by convention, again, there's nothing special about this except it's the way that everyone does it. You always draw shear and bending moment diagrams from the left side to the right side. Okay. Shear at any point is equal to the sum of the loads and reactions from that point to the left end. So you'll start on the left end, and if you have a load, and we'll go through an example. There'll be an example on the next slide or two, and then we'll work through that rather than me making up numbers. Magnitude of shear at any point is equal to the slope of the moment line at that point. That's useful in drawing the moment diagram, and we'll see that. So, but in general, the thing to remember is if you know the loading diagram, and what is the loading diagram? The loading diagram is just the free body diagram that shows the external loads, the applied loads, and the support reactions. For the loading, shear, and bending diagram, it's only dealing with the vertical forces. But for most beam problems, there are no horizontal applied loads and there are no horizontal support reactions. Shear at any point is you always start on the left side. So here is the load diagram. Here's the shear diagram, and here's the moment diagram. Loads and reactions acting upward are positive. So again, there's nothing special about this. It just happens to be the way everybody draws them. So if a load or a reaction is upward, it's positive. If it's downward, it's negative. So what does that mean? That means in general, the applied loads in a problem are shown as negative, and the support reactions are shown as positive. Shear diagram is straight and sloping over uniformly distributed loads. And that is, of course, because the shear is the first derivative of the load. So therefore, if the load has a constant, value, then the shear is going to have a constant slope. The shear diagram is straight and horizontal between concentrated loads, and shear is a vertical line at points of concentrated loads. And we'll go through examples that show these. Then, the majority of the things we just said and the relationship between the load and shear is also equal in the relationship between the shear and the bending moment. If you know the shear diagram, then the bending moment diagram can be drawn. The bending moment at any point is equal to the sum of the moments and couples from that point to the left end. What that really means is you start at the left end and you work your way towards the right based upon what you're seeing in the shear diagram. Just like in the shear diagram, you work your way from the left to the right based on what you see in the loading diagram. Clockwise moments are positive. So again, you have to have a sign convention that clockwise moments are positive, counterclockwise are negative. And the magnitude of the moment at any point is equal to the area under the shear line up to that point. Okay. The maximum moment occurs when the shear is 0. If you remember your calculus class, that's because there is a local maximum there where the slope becomes 0. Bending moment diagram is straight and sloping between concentrated loads. The bending moment diagram is curved between uniformly distributed loads. When the shear is decreasing, the diagram is concave downward. When the shear is increasing, it's concave upward. These are the kind of things that my structures professor used to lose me on. But the good news is, I don't think on the PE exam, your knowledge of the construction of shear and bending diagrams bending moment diagrams is going to rely on the stuff like the concave upward and concave downward stuff. It's going to test whether or not you understand that the shear diagram is the sum of the loads from the left side up to that point. The bending moment diagram is the sum of the shears from the left side up into that point. That where the shear is 0, a local, a maximum occurs, and things like that. The stuff where you're trying to sketch in the second and third order parabolic shape, I just don't see how the PE exam could test that.
Did you say where the shear is 0, that's maximum limit?
Yes. Okay, so here's an example, and because we're running so behind, we'll just go through one example, and there'll be like 5 more that you can work through on your own. And again, if you have any questions when you work through those, you can shoot me an email. But again, I think that the way to learn this stuff is to work through the problems and write those solutions out by hand. That really helps a lot. So you have a point A, where you have a upward load of 24 kips. The total length is 24 feet, is broken up into 6-foot sections. Here, you have a support reaction at point B, you have a support reaction at E, and you have a uniformly distributed load between C and D. The first step is always, on these problems, global static equilibrium. Because we have no horizontal loads, we have no horizontal reaction, so it doesn't really matter to us if the roller connection is here or here and the pin connection is here or here, because they're both just going to have a vertical reaction force. So when you solve the equations of equilibrium by statics, you get that the support reaction at B, well, let's go to the next page. It shows it.
Well, the next page is the diagram.
Okay, cool. Okay. Yeah, so it shows us that the reaction at B is 26 downward. So because it's downward, it has a negative value. The reaction at E is upward and has a value of 14. So 26 down, 14 up gives you a total of 12 down. Right? Is that right? 26 down and 12, yeah. So here you have 24 up and 12 down again. Yeah. This is 2 kips per foot times 6. All right, well, we'll go through it step by step. Okay. So we know on the loading diagram, we have a load. Let's see if this works, red. Okay, so we have an upward 24. Nope, that doesn't work very well. So we have an upward load of 24. That one works even worse. We have an upward load, there it is, of 24. Here we have a downward load of 26. Between here and here we have a distributed load of 2 per foot. And at this end we have a concentrated load of 14. Okay, so for the shear diagram, you simply, let me bring this out a little bit so everybody can see it. Okay. you simply start at the left side and draw what you see. So we start with 24, a positive 24. On one of the slides prior to us, it says that the shear diagram is horizontal between concentrated loads. We have no downward shear between this point and between point A and point B. Therefore, the shear remains a constant value of 24 until we get to here. Now we have a negative or downward force of 26, so we go down. And remember, it also said that locations of concentrated loads, the shear diagram is a vertical line. So we go 24 minus 26, so now we go to minus 2. And this is A, B, C, D, and E. Between B and C, we have no loads, so it remains a constant at negative 2. Okay. Now, between C and D, the load is 2 kips per foot. So what is that total then? Well, it's 6 times 2, so it's a total of 12. That means so we're still at minus 2. So we up to 24, stays constant 24, goes down to minus 2, stays constant at minus 2. Now over a distance of 6 feet, the total load is 12. That means when we get 6 feet over, it's got to be at minus 14. And because it's on one of the other sheets, it says that when you have a uniformly distributed load, the shear varies as a straight line or has a constant slope. So now you just draw a straight line down to minus 14. Now you have 0 force or load between D and E, so it remains a constant at minus 14. And then the reaction at E is a positive 14, and it closes out. So this is a good example for a couple reasons. One, it shows both the way that you translate concentrated loads into a shear diagram, how you translate uniformly distributed loads into a shear diagram. 2, it also says that if the structure is in static equilibrium, it starts at 0 and it closes at 0. So if you draw a shear, if we would have drawn the shear and bending moment diagram, and for some reason when we got here we weren't at negative 14, we were at negative 12. And then we had this support reaction of 14 and we stopped up here at 2, we would know that we did something wrong, because that can't be right. So shear and bending moment diagrams start at 0 and they end at 0. And you don't even have to understand structures. You just have to understand a few simple rules with how you take what you see here and you draw it. You have a concentrated load here, therefore you have a concentrated shear. You have no load, so therefore the shear is unchanged. You have a concentrated load, so you have a concentrated shear. The magnitude is simply what the magnitudes are. Between here and here, you have no load, so it stays the same. Between C and D, we have a uniformly increasing load, but we know, because it's uniform, that the shear diagram is going to have a constant slope or a straight line. And we know that the total has to be 2 times 6 equals 12. So you don't even really have to think about this having a slope of minus 2 if that's the way your brain works straight. But you can also just say, well, I know it's going to have a total of 12. So minus 2 minus 12, it has to be minus 14. So you know straight down from D, you're going to have a point at minus 14, and those have to be a straight line. There's no load between here and here, so it remains unchanged. And then you have a concentrated load here. You have a concentrated shear that has to close at 0. For the bending moment diagram, you do pretty much the same thing. You follow the same sets of rules. Here now you have a constant shear. It looks like that constant load. So you know, so it starts at 0, it has a magnitude of 24, and it has a length of 6 feet. So what's 24 times 6? It's 144. Therefore you know that it starts at 0, and if you come straight down from B, here it has to be 144. And then because it's uniform, then this has a uniform slope. So a uniform a value on the shear line means a uniform slope on the moment line. A uniform value on the loading line means a uniform slope on the shear line. Now, okay, so now what you have on your shear diagram is a constant of -2. But really, what is that? Well, that's 2 times 6, right? Because the same way that this value here is 24 times 6 equals 144. So the change in the first 6 feet has to be a positive 144. Here you have you got a -2 times 6 equals -12. That means the change over 6 feet has to be a change of -12. So 144 minus 12 is 132. So the value after 6 more feet has to be 132. And again, because that is uniform, the slope will be uniform. In other words, the slope will be a straight line. Now between point C and point D, here's where you get into the concave upward and concave downward stuff. But you notice even when drawn properly, it's a pretty slight curvature. What is the area of the triangle here? Because because these are integrals of the prior line, what that really means is the change is equal to the area under that same portion of the preceding curve. So here the area of the shear diagram between points A and B, the area under that curve is 144. Therefore, numerically, the value here is 144. The area under this curve is -12. That means the value numerically, the change is -12. So it's the same principle here. What is the area here? Well, this is a rectangle that is 2 times 6. And it's also a triangle that is 12 times 6. Right? Okay. So really, the area there is minus 48. Right? Yeah. The area under that curve is minus 48. So you know here that the area of the triangle equals 140 equals 48. So you're going to reduce this value from 132 to minus 48, and that is because I'm trying to go fast. Is that a 84 or 60? Yeah, 84. So the value is 84. Now, technically, it's not a straight line because it's a second order curvature. But I think for the point of the exam, if you were to draw a line, that would probably be fine. If you look a couple slides back, it gives you a rule for when you have a decreasing shear is concave upward, or what's that rule? That-
Shear is decreasing, concave downward.
That's right. Okay, so shear is decreasing, so it's a concave downward. So instead of being a straight line here, it's a line that has a little bit of curvature downward. I don't think on the PE exam you might need to conceptually understand that, but you won't be tested in your ability to draw that. Then between D and E, you have a constant shear. There's a total magnitude. The total magnitude of the area under the curve better be 84, because we know that we have to close it out at 0. And in fact, that's what you find there. And that is a straight line. So essentially, every shear and bending moment set of diagrams can be drawn exactly like that. And we did not use structural engineering one time. Okay, so there's lots of examples here. And there's also step-by-step of what was done in the examples. So I invite you to read through it and make sure that you understand them all, because there are some good examples here. Yeah, so if you work through all these, you'll be an expert in drawing shear and bending moment diagrams. Okay, now to close out, here are some tips for the structural analysis stuff. You should always draw, well, not always. It's usually helpful to draw a free body diagram if there's not already one provided. Remember, a free body diagram only includes external forces. External forces are applied loads and support reactions. Support reactions are obtained using the principles of static equilibrium. You can't have more than 3 unknowns. You can't have more than 3 unknown support reactions. In general, beam equations can be used to always give you the shear and moment, the deflection and rotation for beam problems. You generally on the PE exam won't need to draw a shear and bending moment diagram to solve a problem. You might be tested on your understanding of how they're constructed, or be able to read a value from them. You might be given a shear diagram and asked what would the bending moment be at some point given this shear diagram. You always start on the left side, you start at 0, and you just go step by step following whatever that portion of the figure is on the previous graph. From a load diagram, you can always draw a shear diagram. From a shear diagram, you can always draw a bending moment diagram. You should pay attention to symmetry. A lot of problems are symmetric, and you don't even really need to use the equations to know what the answer is. There's no horizontal loads, therefore there's no horizontal reactions. Half of the vertical load will be carried by each side, that sort of thing. If there's a concentrated load or a loading pattern that is non-symmetric, but it's simple, then the reactions can be simple proportions. For your stresses, essentially for the axial stresses, for the internal stresses, generally there'll be axial loads and there'll be bending loads. So the 2 equations that you use is load divided by cross-sectional area, or MC, over the moment of inertia. Determine the length over which the load is applied. Follow the load path. Remember, the load path goes from the top of a structure down the roof let's say, for a bridge, you'll have the deck. The deck will be supported by girders. The girders will be supported by beams. The beams will be supported by foundation, which if we ever finish this, we'll talk about. There is the allowable stress design method, right? And that is where basically you do not put a factor on your loads. You are basing the design on the maximum strength, and you're applying some sort of factor of safety, as opposed to the load reduction factor approach, where you're applying load factors on what you know, you're applying factors to what you know less about. And what you know less about are what are the magnitudes of the loads. You apply a larger factor on live loads, usually multiply it by a factor of 1.7, and a smaller one on dead loads, multiply it by a factor of 1.4, and that's because when you boil it down, you can talk about a lot of other things, but a dead load is a load that you know with certainty what it will be and where it will act and when will it act. A live load is a load that you have less certainty about what the magnitude will be, where it will be applied, and will it always be applied. Okay, so here's an example of a design moment for a beam. We don't have time to go through it, but essentially this is a wall. It's being supported by, it's a floor. It's a floor with a wall. Ouch. It's being supported by 3 beams. Each beam has a tributary area that contributes its load, and you work through what is the total factored design moment on the beam. So when you work these equations on the exam, you have to look for the word factored. Sometimes it will ask for the unfactored design moment. Sometimes it will ask for the factored one. For the factored one, essentially all you're doing is, for that case, you separate the dead loads out from the live loads. You apply the beam equations using what the loadings are, and then you just apply a global factor of 1.4. I'm sorry, for the dead loads. For the live loads, again, you use the unfactored value in your beam equation, and then you apply a global factor. See, it's cleaner this way. It's cleaner so that you don't get confused. Instead of going into each time that you apply the beam equation, putting this factor on your load amount. It's simpler and cleaner, I think, to use the unfactored loading that's in the problem statement in your beam equation, or even in your shear and bending moment diagram if you chose to solve the problem that way. And then once you get an answer, then multiply that answer by 1.4. That way you know that you wouldn't be applying that you're applying the 1.4 or the factor once and only once. So that's an example to go through. Here's another example of a masonry wall that has axial loading, and you can work through that. And it's a problem here. And then there's a third example of a basement. This is, although it's a basement wall, really what it looks like is a cantilever beam standing on its side with a fixed end here, and you have a lateral earth pressure there that we will talk about shortly. And it is essentially a triangular load that is a maximum at the fixed end and goes to 0 at the free end. And that's it. So, earth pressures and retaining walls and slope stability. For the most part, most of the emphasis is on shallow foundations and lateral earth pressures and retaining walls, because those are what lend themselves to the types of problems that are on the PE exam, more so, and they're sort of the most fundamental and the most commonly used. So everything we talked about in the structural 2, see, it's interesting, because usually I teach the geotechnical 2 class first and then the structural 1, but now that we did the structural class 1 first, I sort of like that more, because we have started with the structure, we've worked our way down, and now what the shallow and deep foundation are, those are just 2 options for how to transfer the load of the structure to the earth. So we'll start with shallow foundations and bearing capacity. My contact information does not change. Look at that. I've got to go twice. All right, so we're going to go with types of shallow foundations. What is an allowable bearing pressure? What is the modulus of subgrade reaction? What are the classical bearing capacity equations? What is the effect of a shallow water table? Eccentric loading, that means loading where the axis of loading is offset from the axis of your foundation. And then some sort of specialized equations for mat or raft type of foundations. There'll be some examples. There we go. Okay, so the most basic type of shallow foundation that you'll see on the exam is a strip or continuous footing. This might be a footing that underlies a wall of a structure. So you might have a load-bearing wall of a structure, and then you would have a continuous footing that coincides with that load-bearing wall that is transferring the weight of the structure to the earth. So in elevation view, is shown like this. What it is, what you're solving is a 2-dimensional slice per foot into and out of the screen. So when you're dealing with a strip or continuous footing, the result you get is per linear foot. Okay. In some cases, it might be, it might have economic advantages to, instead of using a strip footing, to use spread or isolated footings. These typically, instead of coinciding with a load-bearing wall, these would coincide with a column of a structure. These are not per foot into and out of the wall. When you're dealing with spread footings, it's a total load. So the continuous or strip footings, you're doing a 2D slice per foot into and out of the screen, per foot for the length of the footing. For the spread or isolated footings, you're looking at a total load or a total force. A combined footing, really all that is if, based on the loading you have and the soil conditions you have, the size of the individual spread footings would be such that they would almost touch each other that it might make more sense just to do it as a single pour. So a combined footing is basically when, based on the necessary diameters or size of the isolated or spread footings, it makes more sense from an economic construction viewpoint to do it as a single. Again, what you would be dealing with here is a total force. So if you have a problem that has a spread footing or a combined footing, the answer you're going to be looking for is a total load, a total force. If you have a continuous or strip footing, the answer you'll be looking for is a loading per foot of footing. A mat or raft foundation is basically takes the concept of going from a spread footing to a confined a combined footing and blows it up, and now you've got numerous columns that you're supporting, and the size of each spread footing would be such that it makes more sense to do it as single continuous structure. Mat or raft foundations also have the advantage of reducing differential settlements. So if you don't have great uniformity in the foundation underlying your structure, you might be concerned that you would get more settlement at this footing than you would at this one here. And it's not economically viable or feasible or advantageous to excavate all that material and replace it with some sort of an engineered fill. So in order to reduce settlements, you do it as a single footing, which sort of just, evens things out. Okay, allowable bearing pressures. So when you design a shallow foundation, like this one here, there are two criteria that are used. Essentially, they're basically designed using the allowable stress design approach, which is you have a maximum strength for the soil foundation, and you're going to limit the bearing pressure you support to some portion of that maximum. And the way you get to that is you take the maximum strength of the soil, you divide by some factor of safety, 3 or 4 or something, and then that is the allowable bearing stress that you design for. That's what lends itself to problems on the PE exam. Those are the kinds of problems you're going to have to answer. You're going to be doing problems that say, what is the allowable bearing capacity for this foundation for a factor of safety of 3? In reality, however, that's really not the way that foundations are designed. The way foundations are designed is based on the tolerable settlement. But those don't lend themselves to the types of problems that are on the PE exam, and therefore I think if you take the geotechnical afternoon portion of the exam, you might be solving problems or working on problems that are incorporating concepts of settlement into a shallow foundation, but generally in the morning problems, you're going to be using the allowable stress design approach and applying some sort of factor of safety to the maximum strength that we will calculate. That maximum strength, so in most cases, settlement governs the design. What that means is, even if you have a factor of safety of 3 here, it won't fail, but you might get more settlement than your building will allow for. That, however, does not mean that that won't be the kind of problem that you saw with the exam. So bearing capacity failure is a concept that's used in the allowable stress design approach. And essentially a factor of safety of 3 is used for most problems, and that's on the dead loading plus the maximum live load. And include in design the dead load, the effective weight of the footing and soil directly above the footing. This is usually not very important because it's small in relation to the bearing capacity, but when you're designing the shallow foundation, you have a certain allowable bearing capacity at the base of the footing, and you take the applied load, you divide by the area of the footing, and that gives you a bearing stress. And you want this bearing stress to be less than the allowable bearing capacity of the soil that underlies your foundation. Technically, this has to also support the weight of the concrete of the footing. And it has to support the weight of the soil compacted above the footing. Usually the weight of this concrete and the weight of this soil is small relative to the total applied load, and it's sort of a negligible thing. So on the problems on the PE exam, it's not certain to me whether or not you'll always need to account for that. But there might be a problem that tests your understanding that the allowable bearing pressure has to also account for the weight of the foundation itself and the overlying soil. But like I said, usually that's small compared to the weight applied by the structure. Tolerable settlements. If you do get a question about settlements, the critical concept of settlements in terms of a structure is not the amount of settlement, it's the amount of differential settlement. There are buildings in Mexico City that the second and third floor are now the first floor. And the first and second floor are basements because the buildings have settled that much. But the buildings are fine because they settled straight down. And that's not a problem. When you get a problem is when one portion of the building settles more than the other, because now this L becomes the hypotenuse of a right triangle, and the hypotenuse is longer than that length, and therefore it must crack. So differential settlement is what leads to cracking, and the differential settlement is simply the maximum settlement of some portion of the structure minus the minimum settlement of some other portion of the structure. And there's a concept of something called angular distortion that takes the difference and divides by the total length. So it's not settlement that's bad, it's differential settlement. Modulus of subgrade reaction can be thought of. We talked about the modulus of elasticity in mechanics of materials. This is just that, but for natural soil. For natural soil, instead of stress and strain, you think in terms of applied load and settlement. And the slope of the stress-strain curve, stress and strain curve, is the slope of the stress-strain figure or plot is always a modulus term. So you can calculate a modulus value for a soil deposit, and then that's how you would base your design on tolerable settlements. So instead of taking the maximum, so in this case, the maximum bearing capacity would be this amount of load here. If you take a factor of safety of 3, you take this load amount and you reduce it by 2/3, and you're basically down to here. Well, by using the concept of modulus of subgrade reaction, you can, instead of just arbitrarily choosing a factor of safety of 3, you can say, well, I want my settlement to be less than 1 inch. Because if my settlement is less than 1 inch, that means my differential settlement will also be less than 1 inch. And really, again, it's the differential settlement that you want to minimize. And then that tells you a more meaningful load value. And then you can back calculate what factor of safety that is against the maximum. And most of the time you would see it's a factor of safety that's greater than 3. And here's just examples of modulus of subgrade values based on different soil types. The way you calculate, though, this maximum bearing capacity is by use of what are really a set of empirical equations. Now, I noticed here I wrote allowable bearing capacity. I should complete that thought equals the maximum bearing capacity divided by the factor of safety. That's what the allowable is. So what you do is you first calculate the maximum bearing capacity, and that's what you get out of these equations here. And essentially, they're simple empirical relationships that have 3 parts. You have what's known as bearing capacity factors: N sub C, N sub Q, and N sub gamma. Now in these essentially how this works is, the most general equation is for that continuous or stripped footing, that is, that you're solving a 2D case per foot into and out of the wall. And that Q ultimate, whenever you see the lowercase q, that means that it's a stress. If you see an uppercase q is a force, and lowercase q is a stress. So these are in terms of a stress. They're not in terms of a force. So, and ULT stands for ultimate. So it's the ultimate bearing capacity, which is another way of saying the maximum bearing capacity. It is equal to the sum of 3 parts. The first part being the cohesion of a soil multiplied by a bearing capacity factor that's related to the cohesion of the soil. So in the Geotechnical 1 class, you should have seen the Moore Coulomb shear strength or soil strength relationship. And that is that the strength of the soil, which is often referred to, which is shown as a shear strength, and that's usually a tau, equals what? Well, it is the cohesion plus the normal stress at that location times the tangent of phi, maybe phi prime, and phi prime, it doesn't matter, it depends on things. But anyways, in general, soil has a strength that's related to 2 parts. There's a cohesion term. The cohesion term, cohesion is really a bad term, but really what it is the shear strength the soil has when there's 0 normal stress. That's really what it is. But you have a cohesion term and you have a term that's related to the internal angle of friction of the soil, so you can call this a frictional term. The frictional term increases as the confining stress increases. So it is useful in a lot of soil mechanics and geotechnical problems to divide the world up into three parts. There are clays and cohesive soils. In those soils, all of the strength is in the cohesion term C, and the friction angle is 0. There are sands, gravels, or cohesionless. Maybe cohesionless is probably more commonly used. Cohesionless. Soils, in that case, all of the strength comes from the friction between interlocking grains. 0 comes from cohesion. And then there are what's known as C-fee soils, and that is ones that get part of their strength from cohesion, part of it from friction. Okay. So the first term is related to the cohesive strength of the soil. The second term is related to the embedment depth of the soil and the unit weight of the surrounding soil. So, and that has a bearing capacity factor called NQ. And then there's a third part which is related to the width of the foundation, and again the unit weight. So gamma is a unit weight, which is in units of pounds per cubic foot. Cohesion is a stress. It's in units of pounds per square foot. And if you look at a dimensional analysis, each of these have units of pounds per square foot, and that's why lowercase q is a stress. So the continuous or stripped footing is the most general case. For a square or rectangular footing, you use the same equation, just slightly altered. So the first step in solving one of these problems is identifying which type of a foundation system do you have. And it's either going to be a continuous footing into and out of the board, like the kind that would underline a wall, or it's going to have isolated or spread of footings that are either square or rectangular or round. Combined a footing of 2, it would also use this because it has a rectangular shape. Matter wrapped foundations are treated another way, and we'll see those. Bearing capacity factors vary with the friction angle of the soil. So once you identify what kind of foundation you have, you then identify what kind of soil do you have. And if it is a C-fee soil, then the bearing capacity factors that you use are a function of the friction angle phi. That's going to be given to you in the problem statement. So the problem statement will identify the type of foundation you have, either through words or through a figure. You'll then identify, is this isolated footings, or is this a stripped footing into and out of the wall? And it will identify the properties of the soil foundation that will be supporting the footing, and it will provide a value of phi. Based on that phi, you can go in and you can get n sub c, n sub q, and n sub gamma, and then you just plug those into your equations along with the problem-specific parameters, and that gives you your answer. So these problems are very, very straightforward. You just identify what kind of foundation do you have, what kind of soil do you have, and then plug all of the values into these relatively simple equations.
Where do you get the cohesion?
That would be
C?
given as part of the problem statement. If you want to, you could even simplify these equations more. Because if you have a cohesive soil where C has a value and phi is 0, so in other words, you might have a problem statement that says there's a foundation in a clay, and the clay has a strength of 500 pounds per square foot. Well, what that is telling you is that is a purely cohesive soil. The phi is 0 and C equals 500 pounds per square foot. It might, and if that's the case, then phi is 0, and if you go back into, they will provide for you on the exam a table of the bearing capacity factors if you need to use them. And if you go to phi equals 0, you'll see that the n sub gamma, or the n sub q term, for phi equals 0 equals 1, and the n sub gamma term, it equals 0. So that's why that prior equation, the bearing capacity factor term has fallen out of this, and the third term is gone. Same thing with these other two. Now here's a note. In reality, if a phi is 0, then what the bearing capacity tables will show is it will show n sub c term of something like 5.14 or 5.74, something like that. And it would imply that that's a constant value. In reality, that's not really true. If you have a cohesive soil, a purely cohesive soil, then really the n sub c term changes with the depth of embedment you have. And it changes in a relationship like this here, where it basically goes from 5.7 up to about 7.5. If, however, and that's all well and good, but if on the exam, if they provide you a table of values, and at a phi equals 0, the n sub c term says 5.7, I would use the 5.7. I would not use this more, accurate or refined relationship here. But is included because it might be useful in some cases. It might be useful if you're doing the geotechnical afternoon portion of class. It might be useful to understand that the n sub c term increases to a maximum of about 7.5 as you increase the depth of embedment. You can also simplify the equations for cohesionless soil. So for a cohesionless soil, now C is 0. So now the problem statement, instead of saying a clay with a shear strength or a strength of 500 psf, is now saying a mixture of sand and gravel, or silty sand, something like that, with a phi or friction angle of 30. Because it said that it's a sand, and because it only identified the value of the friction angle, that's your clue that tells you it's a cohesion soil and C equals 0. Just like if it says it's a clay and only gives you a single value of strength, that's your clue that the friction angle phi is 0 and it's a cohesive soil with that given value of C. Well, If C equals 0, then that first term drops off, and now you're left with just the second two terms. So again, all you're doing is you're identifying the type of footing you have, you're identifying the type of soil you have, you're identifying which simple equation that you use, and then everything that goes into that equation comes right out of the problem statement. The reality is, if you have a cohesionless soil, you really don't know what the phi angle is, because you cannot take a representative sample of that into a lab and test it. You might have in the Geotechnical 1 class talked about something called the standard penetration test, which is an in situ field test that is used to correlate what's known as blow counts that are measured from a drill rig in the field to the strength of the soil. If you have a problem that describes a gravel or sand, it might, in the problem statement, instead of describing the soil strength with a value of phi, it might describe the soil strength with a value of SPT blow counts. If it does, then you can calculate the allowable bearing capacity by use of this equation here. Now, this is an empirical equation that has units of tons per square foot. These other equations work as long as you're using a consistent set of units. It gives you the right answer. This only gives you a value in tons per square foot. But it's 0.11 times some correction factor Cn times the blow counts that would be provided in your problem statement times the area of the footing. This correction factor Cn, what it's intended to do is to normalize the SPT blow counts to what they would be if the effective vertical stress at the point of interest were equal to 1 atmosphere of pressure. What's that? 1 atmosphere of pressure is about 2,000 pounds per square foot. It's about 14.7 psi. It's about 100 kPa. So what this is doing is normalizing this value of n to a value that it would have if the effective stress at the location of interest were equal to 2,000 pounds per square foot. Now, in Geotechnical 1, you would have covered what is effective vertical stress. Effective stress is shown as sigma prime, and it is equal to the total stress minus the pore water pressure U. So to use this equation, what it requires is you go to the base of the footing and you calculate what the overburden is, and the overburden is just the vertical stress of soil overlying that point. You subtract any pore water pressure if you've got a water table there, and then you put that value in here along with 1 atmosphere of pressure in the same units as the effective vertical stress. So normally this would be in pounds per square foot. So PA would then be 2,000 pounds per square foot, because 1 atmosphere of pressure is about 1 ton per square foot. And then if you do that, then, so essentially if the effective stress is less than 2,000 pounds per square foot, this is going to be a number greater than 1, and it will make your n values greater. And if the effective vertical stress is less than 2,000 pounds per, is more than 2,000 pounds per square foot, this is a number less than 1, and it makes your blow count smaller. So I feel like the only time I get to breathe is while I wait for the slide. with me. There we go. Too far, there we go. So here's an example of a foundation. This is shows the foundation and geotechnical data for a square footing. To achieve a factor safety of 3, the allowable bearing capacity is most nearly what? Okay, so we know it's a square footing. So we know that the equations we're going to use are the second set. Remember them, or the second line. The first one was a continuous strip or strip footing. Second one was circular square. It was square or rectangular, and the third one was circular. It's a square footing, so we know we're going to use the second one. The unit weight of the soil is 115 pounds per cubic foot. The cohesion is 200 pounds per square foot, and the friction angle is 20. And the problem also includes a table of bearing capacity factors. So already we know that the phi is 20, so we're going to be using 14.8, 6.4, and 5.4. And then you simply identify you have a square footing and a C phi soil, so you're going to use the full equation that doesn't have any of these factors dropped out. And you determine what the bearing capacity factors are, you input those into the simple equation, and you get the answer. Now that answer is, like the ULT stands for, the ultimate or maximum bearing capacity. So when we have that load settlement relationship shown on the screen, that's the value at that peak. But that peak is probably quite a bit more settlement is required in order to mobilize that amount of strength. So we are using the allowable stress design approach with a factor of safety of 3. So you take this ultimate bearing capacity and you divide it by 3, and you get 2187 pounds per square foot. So that's 2187 pounds per square foot. And this is a square footing 5 foot by 5 foot. So you could also be asked, what is the maximum load that this footing can handle? And that would simply be 2187 pounds per square foot times 25 square feet. And then that would be a total load in units of pounds. So a problem like this that has an isolated footing, a square or round, it might ask for the allowable bearing capacity as a stress, or it might ask for the allowable bearing load in terms of a force. Effective shallow ground. So far when we've been talking about these things, we haven't talked about where is the groundwater table. We know in general that saturated soil is not as strong as dry soil, but nowhere in these bearing capacity factors or these strengths do we account for what are the pore water pressures, for example, and how that affects it. The way you adjust these bearing capacity equations for the effect of the groundwater table is in your use of the unit weights. In general, there are 3 cases, and every case is somewhere equal to or in between these cases. There might be a case where the groundwater table is at the ground surface. There might be a case where the groundwater table is at the base of the footing. Or it might be a case where the groundwater table is far below the base of the footing. If you go back to the bearing capacity equations, you'll see that there is a unit weight, a gamma, pounds per cubic foot, in the second term that involves the bearing capacity factor NQ, there's also a gamma in the third term which involves the bearing capacity factor N sub gamma. If the groundwater table is at the ground surface, in both terms you use what's termed a buoyant unit weight. What the buoyant unit weight is, it is the saturated unit weight of the soil subtracting out the unit weight of water. The unit weight of water is of course 62.4 pounds per cubic foot. And the buoyant unit weight is and the saturated unit weight of soil is usually about twice that. It's about 120, 130 pounds per cubic foot. So you're usually going to have a value of about 60-something pounds per cubic foot. And that is smaller than what a moist or dry unit weight usually is. A dry or moist unit weight is usually about 90, 100, 105, 110 pounds per cubic foot. So you can see that use of the buoyant unit weight in both of these terms is going to drive down the ultimate bearing capacity. So having a higher groundwater table reduces the bearing capacity of the soil. If you have a groundwater table at the base of the footing, you use the moist unit weight or the effective, the normal, the dry moist. In a problem statement, it might refer to it as a dry unit weight. Well, if it refers to it as a dry unit weight, then it might be a volume of phase diagram problem. But anyways, hopefully it's not. That you don't have to use the water content and specific gravities and things like that. Hopefully it'll just say the unit weight above the water table is this, the unit weight below the water table is that. If so, then the first term, the NQ term, uses the unit weight above the groundwater table. And because that term, N sub Q, Q is sort of, in geotechnical engineering, the universal symbol for a surcharge. So really this second term, so that first term that has an N sub C term, that's the strength of the soil, that's the bearing capacity of the soil related to the cohesional strength of the soil. The second term is the bearing capacity of the soil that's related to the surcharge weight overlying that point. And the third term is the bearing capacity strength related to the actual strength of the bearing soil underneath your footing. So in the second term, you would use the unit weight above the water table, and in the third term, you would again use the buoyant unit weight because that's where the water is, that's where the soil is saturated. If the groundwater table is, is relatively far below the footing, about equal to the depth of embedment or greater, or the width of the footing or greater, then you just use that dry or moist unit weight in both parts of the equation. So you identify what kind of foundation system you have, you identify what kind of soil you have, that tells you what equations you use. You then identify the location of the water table, and that tells you which unit weights do you use in the two parts of the equation that include unit weights. That's all you have to do to calculate ultimate bearing capacity. And the ultimate bearing capacity divided by a factor of safety is the allowable bearing capacity that you have at the base of your footing. Here is an example of the ultimate bearing capacity for a dry sand. So it provides for us, it's called a dry sand, so immediately we know that its cohesionless C equals 0. It provides a value of phi, and it provides a single value of unit weight, 130 pounds per cubic foot. That's a very dense dry sand at 130 pounds per cubic foot. That's probably a gravel, actually. But anyways, the depth of embedment is 5 feet, and the width of the foundation is 10 feet. That's all the information you need to enter into this equation, and you get an answer of 35.7 tons per square foot. That means every square foot of foundation can support 35 tons. Sand is very strong. Compute bearing capacity if the bottom of the footing is 10 feet below the ground surface. So now instead of having a depth of embedment of 5 feet, you have a depth of embedment of 10 feet. Well, when you do that, you see that the bearing capacity has gone up. So that's a general rule that as the depth of embedment increases, the bearing capacity increases. And as we already talked about, as the groundwater table rises, the bearing capacity falls. Okay, if you have a case of eccentric loading where the axis of symmetry of your load, yes.
Just back to the previous example,
Huh?
for the units for the for those ultimate bearing capacity,
Okay.
always in tons per square foot.
No. See here, this is pounds per cubic foot, but they divide it by 2,000 to convert it into tons.
Yeah, that's what I wondered. 'Cause
Yeah.
the answer is always in.
That you don't have to. The answer is going to be whatever your units of gamma are. In general, your units of gamma will be in pounds per cubic foot. Therefore, your answer will be in pounds of cubic foot unless you convert it to tons. And what they're doing here is they're converting pounds to tons there. Same thing there, they converted to tons. So if you didn't have this here, this answer would be 104,000.
So is it like standard practice to put it in? tons per-
Yes, because your load that's applied is usually not given to you by the architect or structural engineer in terms of pounds. It's usually in terms of kips or tons. If you wanted to do it in kips, instead of dividing it by 2,000, you would divide it by 1,000. Okay, so if the axis of symmetry of the loading does not align with the axis of symmetry of the footing, you don't get a uniform contact stress at the base of the footing. What you get is, as the load goes to one side, the contact stress on that side of the footing increases. And the contact stress on the other side of the footing decreases. Now, why is that important? That's important because if it were at the center, you would have a uniform contact stress of about right here. But when it moves off to one side, what happens is you increase the contact stress on one end and you decrease it on the other end. But now this is now what you have to compare to your allowable bearing capacity. So instead of simply being able to take the load and divide the load by 25 square feet for a case of a 5 by 5 square, now the maximum contact stress or the maximum bearing, the maximum bearing load or the maximum bearing stress will be greater than a simple calculation of the total load divided by the area. And the way that you do that is you simply, if the more than one way to describe this, but the best way to describe it, I think, is to say that what you have here is some offset distance E. If that remains, if the symmetry of loading remains in the middle 1/3, the middle 1/3 of the footing, then what that really means is that it's less than b over 6, right? Because you have a 1/6 on one side and a 1/6 on the other side. What that really makes is a middle 1/3. So saying E is less than b over 6, because that E can be on either side, what that's really saying is that the symmetry of loading is within the middle 1/3 of your footing. If that's the case, then you increase the contact stress by this factor 1 plus 6E over B, or 6E over B plus 1. So now, so if you had a case, that other case where the contact stress was 2,500 pounds per square foot, that was the allowable. Now, instead of being able to design for that 25 something, that 2,500 for the bearing capacity, we would now have to reduce it by a factor of 6E over B plus 1. When you look at that, if E equals 0, then that term is just 1, right? So if it's greater than 1b over 6, in other words, if the symmetry of loading falls outside of the middle 1/3, that's not a good thing, because what that does is that creates a 0 contact stress. What 0 contact stress means is that it has a tendency to want to rotate or turn over. So you always want to keep the symmetry of loading within the middle 1/3 of your footing. When we look in a few minutes at retaining walls, we'll also see you want to keep the resultant force, the resultant vertical load on a retaining wall within the middle 1/3. And if you're within the middle 1/3, then you always have a contact stress along the full width, and then your structure can't turn over because it's got a contact stress there. If it falls outside of the middle 1/3, then your structure can fall over because it's got some area at the end where there's no contact stress holding it down. So that's how you handle eccentric loading. If it is outside of it, I don't know that you would have a problem. It's certainly not in the morning part of the exam where the offset is that great. You might have a problem though where it shows loading like this, and you have to understand that the contact stress increases by a value of 60 over B plus 1, as a factor. Okay. If you have a mat or raft foundation in a cohesive soil, here's how you calculate the factor of safety. Essentially, you take the total load that's applied to the mat. If we remember that figure, the mat or raft foundation was one where essentially it's a slab. and the columns of, or the walls of the structure have a rigid attachment to a slab, and it's used if generally the area of spread or isolated footings would encompass greater than 1/2 of the footprint, or if you're concerned about differential settlement and you want to minimize that. Okay, so if you take the total load applied, divided by the area of the foundation, you subtract that by the unit weight of the soil that you've excavated out, multiplied by the depth of embedment that you've excavated soil to and are embedding the foundation into. If you divide that into the product of the cohesion and the bearing capacity factor n sub c, and this is that same note that was on the prior slide, that will give you a factor of safety, and you want to design it so that the factor of safety is greater than 3. But what in this can you control? The cohesion is whatever whatever nature put there. N sub c, you're probably stuck with 5.14 if you're doing it on the exam. The total load is whatever the load of the structure is. The area of the foundation is whatever the footprint of the structure is. The unit weight is, again, whatever nature put there. The only thing you can control as the designer is the depth of embedment D. So basically the way that you design these is you increase the depth of embedment D until that equation yields a factor of safety of greater than or equal to 3. And then you're done. There is a concept of a foundation that's fully compensated. What fully compensated means is that the weight of the structure that it will be supported is equal to the weight of the soil that was excavated. If that's true, then the foundation can't fail. Well, it could, depending on how much you screwed it up when you excavated it. But the concept is, if your structure weighs 100 tons, and you've excavated to a depth where the weight of the soil that you've excavated is also 100 tons, well, then what have you changed? You haven't changed anything. That soil that is supporting your foundation is feeling the same weight that it's always felt. So you don't ever have to excavate greater than that. So you excavate until you get a factor of safety of greater than 3, or until the weight of the excavated soil is equal to the weight of the load that you need to apply. Or the weight of the load that will be applied. If you have a matter wrap foundation on a cohesionless soil, generally what is used probably as much as anything else is a relationship based on these standard penetration test blow counts, where this is the same equation as before, but the 0.11 that's used for normal shallow foundations is replaced by 0.22. In other words, it's saying that when the foundation area is the full footprint of the structure, then is about twice as effective in carrying the load. So, yeah, that's that. And we have an example here of a matter raft foundation example of a clay soil. What should the foundation depth D be for full compensation? In other words, again, a fully compensated foundation is one where the weight of the soil that you have excavated is equal to the weight of the structure you're trying to support. And it turns out that for this case, if you excavate 20.5 feet, then you have a fully compensated foundation. That's a pretty deep excavation. In order to get a factor of safety of 3, you need to excavate 14 feet. Okay, so deep foundations. That was shallow foundations. What deep foundations are, they're like piers or driven piles. The resisting forces associated with these piers and piles come in two parts. There is the side friction, and there is the tip resistance. So in general, the bearing capacity associated with deep foundations is a sum of the friction along the side. So as you're trying, we'll look at a figure here. So the types of deep foundations that there are piles. Piles tend to be small diameter and drilled into the ground. And then there are large diameter piers and drilled shafts. All the freeways that you see around town, around the Phoenix area, are supported on drilled shafts. Large diameter, basically holes drilled in the ground and backfilled with concrete. And that's because of the types of soil, that's because of the alluvial soil conditions that are prevalent in the Phoenix area. In locations that are more clay, more cohesive soil, it becomes more economical to drive drive in smaller diameter piles. You don't see too many piles around the Phoenix area. It's mainly all large piers and drill shafts. But regardless of which one of those you have, the concept is the same. The ultimate bearing capacity is equal to the sum of two parts, the skin or side friction and the point or tip resistance. Again, the allowable bearing capacity equals the ultimate bearing capacity divided by the factor of safety. So just like on the shallow foundations, when we calculate when we use equations for the bearing capacity for deep foundations, what you're calculating is the ultimate or maximum, and to get the allowable, you divide by a factor of safety. There are a couple methods that are primarily used to calculate the side friction and the point or tip resistance. One of those is known as the Terzaghi method, and that is shown here in two parts. So the side friction is C. C is the pile circumference, which is sure to trip on somebody up after we've driven it into your head over and over again. The C is a cohesion term. But in this particular equation is a pile circumference. And then it's the sum of this value here. K is the lateral earth pressure coefficient that we'll talk about in a few minutes when we talk about retaining walls. Sigma prime is the effective stress inside that layer, and a delta term here is the friction between the pile and the soil layer. So why is that a summation? That's because the side friction can pass through various layers. So if you have a problem where you're doing a deep foundation, layer 1 might have a certain C and a certain phi, layer 2 might have a certain C and certain phi, layer 3 might have a certain C and a certain phi, and then there might even be a layer 4, and there might be a groundwater table somewhere in here. So the side friction, you calculate for each of these layers. Essentially what you're doing is you're unwrapping the circumference of the drilled shaft or pile, and you're calculating the friction between the soil and the circumferential surface area that passes through each of the layers. So you would do this for layer 1, you would do it for layer 2, you would do it for layer 3, and you would do it for layer 4, and you would, well actually there was a 1 up here too, you get the point I think. And so there would be a certain amount of skin friction here, a QS. There would be a certain amount of skin friction for that layer, and you would sum them up, and then that would be the total amount of skin or side friction that is resisting the applied load. Then when you get to the base, the end bearing is equal to the effective stress times n sub q, so that's the bearing capacity factor term. So the Tuzagi approach actually uses one of the bearing capacity terms that's used in shallow foundations. And then the area, AP is a cross-sectional area of your pile. So this first one, you sum. See, what you're taking here is the pile circumference, and you're multiplying it by the friction. So when you take the friction in terms of a stress, you multiply it by the circumference, what you're getting, well, you also have to multiply it by the length through each layer, but you're getting layer by layer by layer side or skin friction. You only have the QP, the end bearing once, because it only occurs one time. So that's why there's no summation on that. So you go through each soil layer that the deep foundation passes through. You calculate a force, a resisting force. Remember that this has units of force because it's a uppercase Q. So you'll get a force for each of the layers, you add them up, and then you'll get a force for the end of bearing. You then add those up, and that's your ultimate bearing capacity. And then you divide that by the factor of safety required in your problem, and that is the allowable bearing capacity using the Terzaghi approach. There is another approach called the Meyerhoff method. The Meyerhoff method is based again on soil penetration test blow counts. So now, instead of characterizing each of these soil layers by a C and a phi value, you're now characterizing each of those by its N value, or its blow count. For each of the layers, the QF, remember this is a lowercase q, so it's a stress. So the resisting stress in each of these layers is in units of tons per square foot, the blow count divided by of 50. So for example, if you had a blow count of 30, then QS would be 30 over 50, which is 0.6 in tons per square foot. 0.6 tons per square foot is 1,200 pounds per square foot. So in that example, if N equals 30, then QS equals 1,200 pounds per square foot. If the circumference of this, well, instead of being circular, let's make it a square. If this a pile is 1 foot square, then the cross-sectional area is 1 square foot. That's why I chose a square. So it's 1 square foot. And if the depth of embedment is 10 feet. Okay, so if this is 1 foot on the side, and the layer thickness is 10 feet, then the circumference is 4 feet. 4 feet times 10 feet is 40 feet squared. So QS1 would then equal 1,200 pounds per square foot times 40 square feet. And you would get 48000. You would get 48,000 pounds. Or you would get, you divide that by 2,000, you would get 24 tons. So so using the Meyerhoff approach for a layer that is 10 feet thick, that is penetrated by the deep foundation, if it has a blow count of 30 and it is 1 foot square, then your side resistance for that layer is about 24 tons. You would repeat that for each of the layers, depending on what the blow count is. And that would be your skin friction. Then to calculate the end bearing capacity, now you're just looking at this layer down here where you have the end layer, and that will have a blow count. Now let's say that's a blow count of 45. You would apply that same correction factor that we saw on a previous slide, that is normalizing the blow counts to a unit, to an effective stress of 2,000 pounds per square foot, or a single atmosphere. And you apply that correction factor to that blow count, and then you simply multiply it by 4, and that's in terms of tons per square foot. So, sort of the details aside, for deep foundations, the solution approach is sum up the side or skin friction for the layers of soil that are provided in your problem statement. And then after you sum those up, add to them the end-bearing resistance of the layer where the tip of the deep foundation is. Here's an example of a single pile in sand. We don't have time to go through it, but it's worked out for both the Terzaghi method and for the Meyerhoff, I think. I think in the next page I do the Meyerhoff too. No, I guess not. No, we just do the, fine, we just do the Terzaghi method in that example. That was for sands. There's also a set of procedures for a single pile in cohesive soils. Again, we're running short on time, so I'll just point out that the concept is the same. The ultimate bearing capacity is the skin friction plus the point resistance. The allowable bearing capacity is always the ultimate divided by a factor of safety. In this case, though, for clays or cohesive soils, you use something, you apply a term that's called the alpha term for the side friction. And the alpha term you find from a chart, and this is honestly the only chart of this value I've ever seen. I think in some places they provide these values in a table, but they're the same value that's shown here. Essentially what this shows is that the alpha value goes down as the strength of the soil increases. What is always confusing to people is that the axis for the alpha value is shown in terms of QU. QU is the unconfined compressive strength. And the unconfined compressive strength, QU, is 2 times the cohesion value C. So although you use C in the equation that includes alpha, in order to read alpha off the chart, you have to multiply C by 2 and go to the chart for QU. And invariably, the number one mistake that somebody makes is they come into this chart using the cohesion of value, which makes the alpha value too high. So you want to make sure that you're multiplying, so the problem statement will include a value of C or CU. You multiply that by 2, and then that's the value you use. You would use this average curve here, and for example, if the cohesion were 500, if the cohesion were 1,000 pounds per square foot, 1,000 pounds is 1/2 of a ton, so then the unconfined compressive strength would be 1 ton per square foot. You come in this chart and you would see the value is about 0.83. And then you go into this equation here, and for alpha you put in 0.83. But although the equations differ, the concept is the same. You're summing the side friction up for each of the soil layers that are described in the problem statement. And then you sum those up, and then you add it to the end bearing resistance, and then that's the total, the ultimate bearing capacity, and then you divide that by a factor of safety, and that gives you the allowable bearing capacity. Okay. Deep foundations are sometimes constructed in groups. So there'll be more than one deep foundation structure drilled or installed, and they'll be tied together by a single pile cap. That's common again on the freeways around town. There are often 2 or more large drilled shafts that are connected by a single pile cap. When you analyze or design a pile group, you do it 2 ways. You do it as an equivalent single pile. So what you have here is 16 small diameter drilled shafts connected by a single pile cap. What that does is it allows a single applied load to be distributed among 16 drilled shafts or drilled piles. If you sort of turn your head and squint, that looks like one large drilled shaft. So you don't know ahead of time how the system will perform. See, if depending on the load that's applied, the characteristics of the soil, and how close the spacing is, you might get what are known as overlapping stress fields, which would basically reduce the effectiveness of each shaft. In other words, if these 4 are too close to each other, they all 4 might be trying to get strength from the same patch of soil. But, you know, there is no free ride. So this soil right here in the center might not be able to provide strength to all 4 of those. So what you do is you do one calculation of a single pile. You see what its ultimate bearing capacity is. You multiply that by 16. That would be an ultimate bearing capacity based on a single pile analysis. Then you repeat the analysis, but now you treat it as a single pile, where now your skin or side friction goes around the outside of them. But you would use the same approach as these pass through various layers. You know, it has a certain circumference around the whole group, and it has a certain depth of embedment. Down at the bottom, it has a certain cross-sectional area, which would give you an end bearing capacity. So you do the single pile analysis, you multiply by the number, and then you do the group analysis, and you compare the 2 ultimate strengths you get, and you use the smaller of the 2, and then you divide that by the factor of safety, and that's how you get the allowable bearing capacity. So there's an example here that you can go through and work through that has layers of clay, and it performs the analysis for a single pile and multiplies it by 12, and then it also does the analysis for the group, and it compares the 2, and we find, I hate to be a spoiler, but the single pile, the capacity governs. In other words, that calculating the capacity of a single pile and multiplying by 12 gives you a smaller ultimate strength than treating it as one structure, and therefore that is the strength that you use, because you really don't know how it will perform. So you want to be conservative. All right, retaining structures and lateral earth pressures. There are gravity retaining walls and there are cantilever retaining walls. This will really be the last thing we talk about. There is information on slope stability and an example problem to work through that I would invite. I think slope stability would be not included as often on the exam, and if so, maybe only one problem. So you'll be able to work through the slope stability, and if you have any questions when you work through it that you don't understand, you can, like I always say, you can send me. All right. The lateral earth pressure is the horizontal stress that's applied by the backfill held up by a retaining wall onto the retaining wall. It is a function of the vertical stress at that point. So at the top of the retaining wall, at the top of the backfill, what is the vertical stress? The vertical stress is 0 at the top of the wall because there is nothing above that point. If you come down 1 foot, what is the vertical stress? The vertical stress is the weight of 1 foot of soil. So if it's 100 pounds per cubic foot, then the weight would be 100 pounds per square foot. So really, the vertical stress anywhere between the top of the retaining wall and the bottom of the retaining wall starts at 0 and it increases linearly and its slope is the unit weight of the soil. So at each location where you have a vertical stress, you have a corresponding lateral earth pressure. And that lateral earth pressure is the pressure that the soil backfill exerts on this wall trying to push the wall out. And that is a simple relationship of the vertical stress multiplied by some value called K. And K is known as the lateral earth pressure coefficient. But what this is saying here is that this vertical stress is the unit weight times depth. What that's really saying is if you have a retaining wall here and the backfill behind it, the vertical stress starts at 0 and is a straight line. That's not a very straight line that I drew, but it's a straight line. It has a slope equal to the unit weight, and the maximum value is what? The maximum value is the unit weight times the height of the wall. That is the vertical stress. Now the horizontal stress that is created from that vertical stress is known as the, like I said, that's the lateral earth pressure, and it is equal to the vertical stress times earth pressure coefficient K. And you simply calculate that earth pressure coefficient K based on characteristics of the soil that's used in the backfill behind the wall. There are 3 general cases for K. There's the lateral earth pressure at rest, there is the active lateral earth pressure, and there is the passive lateral earth pressure. In the problems you will see, the lateral earth pressure at rest will only be used if you have an explicit statement in the problem statement that says the structure will not move. So it has to say something like it's rigid or is fixed or won't move. If that's the case, then the earth pressure is calculated based on something called K0, and K0 is basically just 1 minus the sine of phi. So if there's a problem that says that the retaining wall is sufficiently rigid so that it won't move, then the problem statement will, or the problem figure will show us a phi value for that backfill. You simply take 1 minus the sine of phi, and that will be the value of K naught, and then you take K naught multiplied by the vertical stress at any location, and that is the corresponding horizontal stress. 99% of the cases that you will have, and certainly on the PE exam, what you will use for the problem state, for calculation of the problem, is the case of A, the active earth pressure. That is the failure state when the wall moves away from the soil mass. People sometimes have a hard time envisioning what these two statements mean. The failure state when the wall moves away, the failure state when the wall moves into the soil mass. What that's saying is, if you have a wall here, and if the wall moves away from the soil mass due to the lateral earth pressure that the backfill is applying to it, if it moves out to here, then what will happen is the soil will slump in. And you'll get a failure slope that sort of looks like that of the soil mass failing down. The relative movement will be this wedge of soil moving down relative to the soil mass. So the failure is in here, and it's the failure state when the wall moves out. That's what that problem statement means, and that's a normal case. When you build a retaining wall, there's a lateral earth pressure that's trying to move the wall out. If the wall's not sufficiently rigid to resist a movement, and if it's not strong enough, then it will move out, and the soil, and there will be a wedge of soil that fails, and that is why you design for the active case. For the passive case, that says what's the failure state when the wall moves into the soil mass. If you had something that was forcing this wall into your backfill, how would it fail? Well, now it would fail mounding up. And you would now get a wedge of soil that would fail upward. If you were pushing this in, the way it would fail is you would get a wedge of soil riding up against that backfill. And that's what's meant by this passive earth case. So you would only design for the passive earth case if you've got something that is forcing your structure into a soil mass. And that is a rather unusual case, and that's why it's not designed for. So 95% of the time on the PE exam, 99% of the time you will use case of A. That's just a chart showing that you don't need very much movement in order to mobilize the active failure case or the passive failure case. Here is a question that tests your understanding of these various Ks. This talks about the system should be sufficiently rigid so that only negligible deformations will occur during the excavation. Which is the appropriate one to use? Because it says only negligible deformations will take place, that tells you that the case of not, the lateral earth pressure at rest, is the one that you want to use. Okay, if you're using Ka 99% of the time, 98% that time you'll use what's known as the Rankine equation. The Rankine equation says that k sub A is the square of the tangent of 45 minus phi over 2. It can also be calculated as 1 minus the sine of phi over 1 plus the sine of phi. So the only thing you need in order to calculate the k sub A or to calculate k sub p, that this should be a k sub p here, or the case of not, the only thing you need to know is the friction angle of your soil. If you know the friction angle of your soil, then you can calculate k sub A, k sub not, or k sub p. 99% of the time you're going to use the k sub A. So the lateral earth pressure is going to be equal to the vertical stress multiplied by k sub A for the vast majority of the time. The problem statements on the exam will tell you to use the active case or use the passive case. Or it will test your understanding of when is the passive case appropriate, when is the active case appropriate, when is the at-rest case appropriate. The Rankine approach has 3 simplifying assumptions: a horizontal backfill, a vertical wall, and no friction between the wall and the backfill. You use a Rankine case on the exam unless there is an explicit statement and problem statement that one of these 3 things is not true. If there is on the problem a diagram, it might show that the backfill behind the wall is not horizontal, but instead it slopes up. It might show that the face of the retaining wall is not vertical, but instead it slopes back. It might provide a value of friction between the wall and the backfill. If the problem statement does any of those 3 things, then you use the Coulomb approach, which is still a simple, relatively a simple equation, but just incorporates more terms. We'll be wrapped up in just a couple of minutes here. So here's an example of how to calculate k sub A for a friction angle of 28 and k sub p for a friction angle of 28. You see k sub A k sub p is much, much, much larger than k sub A. And that makes sense because it's going to take a lot more force to move this wedge upward than to push the wall out far enough for it to slump down. And that's why k sub p is so much, much larger than k sub A, and that's why it's insane when people say, well, you should always design for the passive case. That's insane. There is, in this case, a factor of nearly 10 on those 2 things. The way that we're running behind, there are lots and lots of examples in here of working out lateral earth pressure problems. In general, here is the approach that they follow. You have a lateral earth pressure diagram behind the retaining wall. For the normal case, you have this triangular stress distribution where the horizontal lateral earth pressure is 0 at the top of the wall and it's a maximum value at the base of the wall. That is a triangular stress distribution. You can replace a triangular stress distribution with a single equivalent force that acts through the centroid of the triangle. So if you calculate the area of this triangle, that is the magnitude of the equivalent resultant force here, P, and it's shown by this equation here. And it acts through the centroid, or 1/3 of the height of the triangle. So you can replace the lateral earth pressure distributions with single resultant forces, because that's what the structural engineer who is designing the reinforced concrete retaining wall, he doesn't want a distributed stress distribution. He wants an equivalent resultant force acting at some point. That's what you get. And for the passive case, you have both a triangular one that's associated with this same thing, the vertical stress multiplied by case of P, but you also have a constant. And the constant is 2 times the cohesion times the square root of case of P. Because it's a constant, it acts the same everywhere along the height of the wall. So that is a rectangular stress distribution. But you do the same thing with a rectangular stress distribution that you do with a triangular one, which is you calculate the area of that rectangle. That's the magnitude of the resultant force, and it acts through the centroid. Now, the centroid of a rectangle is the height over 2. So for the passive case, you have 2 resultant forces. One that acts at 1/3 of the height, one that acts at half of the height, but the magnitudes are shown right here, and I've worked it out. Here's an example of, now when you have an aerial surcharge. If you have a surcharge up here, there's a reason why they build a retaining wall here. The reason they build a retaining wall here is either to open up space here or to support space there. If you have a structure up here, it applies a surcharge load. That surcharge load is Q. That surcharge load is felt everywhere along the length of the wall. If I stand here and somebody stands on my shoulders, and somebody stands on their shoulders, and somebody stands on their shoulders, that top person, everyone feels his weight, right? This surcharge that's applied here is felt everywhere along the height of the wall. So it becomes, again, a rectangular stress distribution, where you have the surcharge load Q as a vertical stress, and you multiply it by K. Again, that's a rectangular stress distribution, so you calculate the area of the rectangle, you apply the resultant force at the halfway point. For a groundwater, this is the last thing that we'll do. For the groundwater table, you do a couple other things. First of all, you start above the groundwater table where you have a dry unit weight. Again, the vertical stress at the top of the wall is 0. It increases linearly until you reach the groundwater table. Okay. At the groundwater table, you then have to split the weight of water from the weight of soil. And why is that? Because lateral earth pressures only apply to earth pressures. No duh, right? Lateral earth pressures do not apply to water pressures. Water pressures have a hydrostatic pressure equal in all directions. So once you get to the groundwater table, you do 2 things. One, the weight of this dry soil above the groundwater table acts as a surcharge load below the groundwater table, because all this soil has to carry the weight of what's up here. So when you increase from 0 to the stress here at the water table, that stress then continues all the way down. Because just like on the prior page, this surcharge is felt everywhere along the wall. however many people stack up on my shoulders, I feel them all. And everybody on my shoulders feels everybody above them. So the dry soil above the groundwater table acts as a surcharge load. So it creates a rectangular stress distribution that starts at the groundwater table, extends to the base of the wall. The weight of soil and water below the groundwater table is split up. The weight of the soil below the groundwater table, you apply a case of A2. The weight of the water below the groundwater table, you don't. So for the case of a groundwater table, things get split up into 4 stress distributions. But again, they are just triangles and rectangles. For each one of them, what you always do is you take the area of the stress distribution, that becomes the magnitude of the resultant force, and is applied through the centroid of the shape. And you'll see that you can have all kinds of, I'm losing my voice. You can have all kinds of variations. And as I scroll through the rest of the pages, you'll see that there are several problems worked out in detail that go through these. And then we go through retaining walls. And what you're doing with the retaining walls is you're just applying the things that we've learned. You're going to check for overturning of the retaining wall. The way you check for overturning is, does the resultant vertical force lay within the middle 1/3? Sliding along the base, whether or not the shear resistance between the wall and the underlying soil is greater than or less than the lateral earth stress is trying to make the move, and will there be bearing capacity failure. So you have examples that work through that. You go through some brace excavations, which I don't even know how important those are on the exam, but I throw them in. And then you'll go through the use of a slope stability chart and detailed examples. I apologize for sort of being behind on stuff, but I think we've worked through all of the concepts that you need, and if you work through all of the problems that remain, you should be able to do well on the exam. And if you have any questions, you can send me an email and I will promptly reply. Good luck on the exam.
Thank you.
You're welcome.